So let me first thank the organizers for the kind invitation. This presentation will be about a work we did with my student Ho-Ung Lee, who made a major contribution to this work. And I should also mention that there are some related works studying the same problem of the how spin relaxes in the framework of perturbative QCD. So we started thinking about this very kind of a simple question, how the spin of basic constituent of quark-gluon plasma would evolve in time with the interactions given by the perturbative QCD in recoupling regime. And as a simple start, we considered just the case of massive quark, which is also related to the fact that, as Chun-Wang mentioned at some point in the last talk, the spin of lambda baryons arise mostly from the spin of the S quark. So hopefully this is a kind of interesting starting point to ask these questions. So yeah. So let me start the discussion by just explaining why do we need to consider density metrics. The point is that the this energy shift due to the spin degrees of freedom is basically order h bar, which means that the quantum correlation time involved is the zeroth order h bar, which is classical regime. So that if we are looking at the time evolution in the classical time scale, this quantum correlation still exists in the time scale. So that what we need to have is not just the classical kinetic theory, but instead a quantum kinetic theory taking care of these quantum correlations existing in the classical time domain. So that's a major idea behind this approach, right? And as we know very well, it is expected that this time evolution equation for density metrics is a sum of the this Hamiltonian evolution term and the relaxational collision-like term. And fortunately, this this Hamiltonian evolution, which should correspond to a free streaming kind of part of the Boltzmann equation, has been already worked out by many colleagues participating here in the audience that helped us to actually focus just on this relaxational part, which we denote by gamma there. And we are going to explain that this collision term, collisional term, which corresponds to relaxation, can be computed in leading log order in QCD coupling constant. So as I explained, we are going to consider a simple case of massive dilute quarks, which means that we are not going to consider the spin statistics theorems here. So basically, the equilibrium distribution is expected to be Boltzmann in our approximation. And I should mention that there has been an improvement on that by Dillon, Koichi, and Yoshimasa. And moreover, to simplify further, we will make the approximation that the system is nearly homogeneous. In other words, we are going to neglect the spatial gradient of x in our computation of the collision term. And since the spatial gradient expansion is equal to the h bar expansion in this way. So essentially, in some sense, what we are computing is a classical collision term, which is called the local collision term. And I should also mention that there have been important improvement on this approximation by Sun Ko and the Chun Dirk and the other collaborators. So please refer to the talks of Sun and Wang on this improvement. So basically, just to give you a kind of a take-home message, our computation indicates that this relaxation rate in perturbed QCD is given by the g to the 4 log 1 over gt, which turns out to be the same order of the typical relaxation rate for the charge transport phenomenon. And in the later part of the talk, I will explain why this has to be the case for the spin transport as well. Okay, So my talk will be somewhat technical in some aspects, but let me try to emphasize the most basic physics behind those technical computation. So now this spin density matrix has been introduced long time ago by many colleagues here. So I will not go into too much detail on that. So we have 2x2 spin density matrix that can be written in some basis. And we are going to use the SZ eigenbasis, which means that the spin operator will be just a Pauli matrix in that basis. And I want to point out that although this density matrix is written in somewhat non-relativistic form, we can always convert that to a more relativistic definition of spin. For example, in the case of canonical spin defined by that way in terms of these spinners, we can just include the effect of the spinners explicitly to relate the non-relativistic spin polarization to a relativistic definitions of spin vectors in that way. So we are not really losing any generality by computing this kind of this 2x2 non-relativistic spin density matrix. Okay. So before really talking about the spin degrees of freedom, let me just briefly remind you some of the aspects of position and momentum in this density matrix formalism. So basically, density matrix is a product of cat state and Bragg state, right? The first P1 part is a cat part, and P2 part is a Bragg part, and essentially this Bragg part is a complex conjugate of the cat parts, right? It's just quantum mechanics. And starting from the momentum basis, if we go to the position basis by doing this Fourier transformation, because of this complex conjugation, this phase factor has the structure of the P1x1 from cat part minus P2x2 from the Bragg part. And because of this relative minus sign between the two, there is an interesting consequence that if we introduce the average variables denoted by R and the difference denoted by A, essentially this expression is the sum of the A variable and R variable, which means that the A variable and R variable have a canonical commutation relations. On the other hand, the commutative relations between R variables or between A variables vanish. Okay, so that's one point. Then, so Right. So then another way of thinking about this, which is totally unnecessary but useful, uh, is to consider this black part in the density matrix as a state in the complex conjugate space of the cat space, which I call H star there. And in this language, this H star part is easily described by the second contours in the Schwinger-Keldysh formalism labeled by 2. But the point I like to make is that because of this complex conjugation, and since the momentum is IH bar times gradient of X, because of that I, this momentum changes sign under this complex conjugation operator. Another way of saying is that this complex conjugation is time reversal operator. So operation, so that the momentum changes sign. So that changes the commutator relations for this in this complex conjugate space. So instead of having IH bar, we have X2 P2 commutator being minus IH bar, from which we can derive the same result of this canonical commutator relations between R variable and A variable. And especially it should be emphasized that these R variables, XR and PR, commute. That means that in this language of quantum mechanics, in the product of original space H and its complex conjugate H star, that where density matrix lives, we can simultaneously diagonalize these two R variables, which means that we can introduce sort of wave functions with in terms of the simultaneous eigenstate of XRPR, and that wave function is nothing but the Wigner function we usually talk about. And because of this canonical commutator between R and A variable, we can easily convert this Wigner function back to our density matrix purely in terms of momentum, if you want, by having this Fourier transform, okay, between XR and PA. And as I mentioned before, we want to consider a kind of simplified case of spatial homogeneous limit, which means that this gradient of XR, which is conjugate to PA, no, I'm sorry, gradient of XR, which is equal to the momentum, PA, should be much less than the characteristic scale of quasi-particles, which is order of temperature. So in that limit, because PA is a difference between P1 and P2, in this limit, essentially what we are considering is the density matrix, which is diagonal in momentum space. So in other words, the density matrix, which is homogeneous in space, is equivalent to a density matrix which is diagonal in the momentum space. Okay? So this is our starting point of our computation. So we are going to consider only this diagonal density matrix in momentum space. Now we have additional spin index X and S prime, and our main focus will be about the time evolution of this density matrix in the spin space given momentum p. Okay. Now, of course, we are dealing with relativistic fermions, so we have to compute everything in a more field in the language of field theory. So, for example, interactions are given by this spinor field psi x, which is written this way with the spinor UPS there, where A is the this annihilation operator of our spin state. Now, since we are going to consider only the dilute limit, we limit ourselves to the just one quark state, which is created from the vacuum by acting this creation operator. But in that case, basically, the problem is a simple quantum mechanical problem of one particle. The only modification from relativity is that the interactions are given by relativistic interaction form, which involve the spinors. Other than that, kind of a basic framework is just simple quantum mechanics. Okay. So, for example, the interactions are given by this relativistic interactions from the field theory Lagrangian. So that it involves the spinor field U and U bar with gamma matrices, but the other than that, it is just a simple one particle quantum mechanics. Now, I should mention that of course there is a more there is a more relevant definition of Wigner functions in relativistic field theory in terms of the spinor field psi. And since the psi field is related to the annihilation operator by this Fourier transform with additional spinor dependence, UP, in general, the positions for psi x, for psi field and the A field are non-locally related. And I think this is closely related to the previous questions about the quantum uncertainty in the position. There is a basic uncertainty due to the existence of spin degrees of freedom in defining what is the actually the physically measurable position and momentum. But another reason to consider especially homogeneous limit is that in that case, since we are really neglecting the space dependence, this non-relativistic Wigner function is actually is simply related to relativistic Wigner function by just additional multiplication of relativistic spinors, which is shown by the bottom equation. So in that sense, we can avoid some of this complexity of the problem, and also it can be directly related to the relativistic formalism of the Wigner functions. Okay, yeah. So basically, we are going to compute this density matrix, 2x2 density matrix in momentum space. And we can easily decompose this 2x2 matrix as a sum of the diagonal parts, no, I'm sorry, the trace part and the traceless part. And traceless part is, which is denoted by the spin vector S, is essentially the average of spin with respect to this spin density matrix. And we are going to compute the time evolution equation for this object in spin density matrix in momentum space. And just to mention, this trace part, F, is nothing but the usual number distribution in momentum space that is used in the usual Boltzmann equation of quasi-particles in QGP. So that would mean that the equation we derive for F would be actually, should agree with the previous computations of the collision term for the usual number distribution function in leading log approximation of QCD. And indeed, we double check that too, okay? So now here comes the kind of main point of our computation, the time evolution of the density matrix. Well, it's simply given by the unitary time evolutions, but the important point to make is that the Bragg part and Cat part of the state evolve with the different unitary matrices because because the gauge fields in the Schwinger-Keldysh contours are different between the two contours, and the correlation functions between these two gauge between this gauge field in the Schwinger-Keldysh contours are usually called Whiteman functions, and they fluctuate in different ways given by the Summer density matrix, so that we should take care of this difference very carefully. Okay, but the basic formalism is just the usual quantum mechanical time evolution given by the unitary evolution operator in terms of the Hamiltonian with interactions with the gauge field. Right. So this essentially this the effect of background quark-gluon plasma are included in these 2-point functions of the gauge field fluctuations of this gluonic field fluctuations, which we denote as G here, and we are assuming that this background is in Summer equilibrium, so that this correlation function should satisfy the this KMS condition given by that, given by this formula here. And also there's no 1-point average for these gauge field fluctuations. So that means that when we in our computation, we have to do a second order perturbation theory in terms of this interaction, which is proportional to the gauge field here. And so if you look at the formula, we are expanding this unitary time evolution operator to second order in the interactions, HI, which contains the gauge field. And there are 3 contributions. One contribution is from the second order terms from, say, 1 unitary operators. And there are 2 of them. One is from the this time evolution operator for Bragg part, and the other is from the cat part. And they represent the self-energy contributions denote in the diagrams B and C. And also there exist cross terms. One interaction from the U1 and the other interaction from U2. One is from Bragg part, one is from cat part, and they represent and those contributions is represented by the diagram A. And it's important to include this cross diagram A to ensure that the total probability of the density matrix is conserved. So only we add all these 3 terms, the unitarity is satisfied. And you can also compare each terms with what is expected in the Lindblad form. And essentially Lindblad form has a very similar structure of this self-energy and the cross terms. Okay, so so now let me just mention that this gluonic 2-point functions in our approach, in our leading node computation includes this hard Summer loop self-energy corrections, which essentially include the hard particles in the background QCD plasma. That means that in our computation, we are essentially considering the scatterings of our massive quark of interest with background hard particles of dominant momentum temperature. And one way of seeing is that if we just cut the diagram, then this hard Summer loop self-energy corrections represent this scattering, the T-channel scatterings with momenta Q, where Q is the momentum of the the 2-point function of the gauge field correlators. Yeah, okay. And let me introduce the spectral density in this way. So this is just definition of spectral density. So G12, which is the Weightman function of the, is given by Boltzmann. It's the Einstein, Bose-Einstein distribution times the something called spectral density, which encodes all the essential data of the hard particles in the background QGP that undergoes the scattering interactions with the quarks. Okay, and this Hadamard spectral density has been known and used for decades, and we are just using those results in our computation. Okay. Now, it is important to discuss about the time scales involved here. So it turns out that the relevant time scale of this 2-point correlation function of gluons is given by GT, because this dominant leading law contribution comes from that scale of Q given by GT. And this time scale GT inverse is much shorter than the time scale of our interest, which is roughly which should be actually larger than the which should be maybe yes. So yeah, let me go to the next slide. Maybe this picture will be more helpful. So each collision has characteristic time scale of 1/GT, and as we will show, this overall scattering rate, which can be thought of as a inverse of the distance between two consecutive collisions, is given by 1/G⁴. So therefore, that the distance between each scattering event is much larger than the duration of the each scattering, which is given by 1/GT. And we are interested in the time evolution in the scale, which is much larger than this time scale of each collisions. Okay, and in that limit, we can simplify this time integration from 0 to the time step delta t, and essentially we can get this linear dependence in the time step delta t if delta t is much larger than the time scale of the correlation function of G. So in that way, we can obtain the time evolution, which is first order in time. And in diagrammatic language, this approximate in diagrammatic language, what we are doing correspond to something called ladder approximation. Essentially, we are neglecting the overlap of the two consecutive collisions, which are far separated from each other compared to the time scale involved for each collisions, so that each collisions can be treated as a single independent event. And in diagrammatic language, this corresponds to ladder approximation. So now let me also talk about a very important aspect, which is quite general in this computation of transport in recoupling regime. So there are two characteristic scattering events. The one class, one type of scatterings involve large angles between initial and final state. Essentially, that means that the momentum transfer from gluon is order of the same order of the incoming momentum, which is t. on the other, and these large scatterings give dominant contributions to the conserved charge transport, such as the baryon charge or the energy momentum transport, like shear viscosity. And on the other hand, it turns out that for the say for other quantities like damping rate and color transport, this small angle scatterings whose angles is less than g are more dominant than the large angle scatterings, and as a result, for those quantities, the relevant scattering rate turns out to be g to the square, whereas for large angle scatterings, it is given by g to the 4. And what we find is that the spin transport or spin relaxation is given by the large angle scatterings, not by the small angle scatterings. And this also agree with the other computations by Kapusta et al. And also by Koichi et al. That I referred to at the beginning of the talk. Yeah.
Oh, sorry to interrupt. So you have 5 minutes left.
Yes, yes, thank you. Yeah. So let me explain why, just physically, why small angle scatterings are actually suppressed for spin transport, so that only large angle scatterings are important. And it was very helpful to discuss on that with Koichi and Dilun last time in Kyoto. So basically, I think the main point, the main reason behind this is that the spin flipping interactions are magnetic interactions between magnetic field and the spin magnetic moment of the quark, and that can be also seen in this golden identity, that the first part, which doesn't involve spin, is not suppressed in small momentum transfer limit, but the second part, which is responsible for this Pauli interaction, which flips spin, is given by the momentum difference between incoming and the final particle. So if the momentum transfer goes to 0 or the angle goes to 0, these spin flipping interactions are suppressed, and this additional suppression seems to be responsible for this large angle dominance of the spin transport. So by working out this somewhat complicated looking expression more carefully, then we can end up to these expressions. So there are a lot of summation over spins, and that computation was quite challenging. And in fact, there was the the major bottleneck in our work, which took us more than I think 6 months, if I remember correctly. But eventually, Ho-Ung found out a kind of efficient way of computing this spin summation. So with that great effort, we were able to analytically compute this complicated spinner summations, and also in this computation, typically it involves this integration of the spectral density respect to momentum. And I only like to point out that this having a finite mass requires us to actually compute something more than what have been known already in the left column. No, I'm sorry, what have been already known for the integer n here. So in other words, with a finite mass, we needed to compute this quantity for half integer n, and it was interesting that those half integer n coefficients also contribute to our final result in the same leading log order. And so with all this computation, I cannot really describe detail. We got this final result, which I will just show you. So basically, the left hand side is the time change time evolution of this density matrix, and right hand side is some operator gamma. And you see that since the divine mass is proportional to coupling constant g, the right hand side is indeed a g to the 4 times log of 1 over g. And this operators, relaxation operator gamma for particle number and spin s, are given by these quite complicated expressions. And there's no point in explaining any detail. I mean, we don't understand what is actually the kind of a simple structure behind this, but at least for the relaxation of the number distribution f, you see that this is given by the total gradient in momentum space. So the number conservation is already guaranteed, which was also quite non-trivial to check. And we also did a couple of very non-trivial checks on this result. For example, the detailed balance in equilibrium is checked, which I should say was quite non-trivial to see. That if we insert this Boltzmann distribution, which depend on momentum through this energy, it non-trivially makes the collision term all vanish. That was quite spectacular to us. And also, we could also check our results by considering a formal massless limit, because in that limit, the spin is aligned with momentum, so that the spin density matrix should be basically proportional to the projection operators defined that way. In other words, the spin density matrix should be a 2x2 matrix dictated by the spin, this chiral projection operators. It cannot be arbitrary. And also, the coefficient functions in front of projection operators, f plus and f minus, should obey the same equation in a parity even environment. And in fact, that means that they actually have to satisfy the same equation of the number distribution f. And quite remarkably again, with this complicated expression for gamma s, we were able to see that indeed in the massless limit, they satisfy the same equation that the number distribution f satisfies. So that was also, I should emphasize, quite remarkable. So yes, so basically that's it. Yes, so our result is just summarized by this one slide, and that's it. Yeah, thank you very much for your attention.
Thank you, Ho-Ung, for this nice talk. And now the session is open for discussion. So I see Dilun. Please ask.
Hong, can you hear me?
Yes, yeah, here you.
Okay, thanks for the talk. So I just have one very simple question. So in the end, when you mentioned that even for this spin diffusion part is when you have this detailed balance, then this F also reduced to the thermal distributions. Is that only in the massless case, or even in the massive case, does it also reduce to the equilibrium distribution?
Are you asking about the spin part?
Yes, spin part.
Yes. So yes. So I think in equilibrium we expect that spin part has to relax to 0, actually, because the density matrix has to relax to identity. So if you see this equation, of course, S equals 0 is a consistent solution of the equilibrium. But what we couldn't check is whether the eigenvalues of this relaxation operator for spin is always such that it relaxed to 0. In other words, we couldn't, I mean, because of this complexity of the expression, we were not able to check whether the relaxation term makes the spin exponentially grow or exponentially decay.
Okay, right. Yeah, I mean, that's basically what we'd expect, right?
Right, yeah.
Yeah, we will expect there should be, quantum corrections to make it polar.
Right. But S equals 0 is a consistent solution of, I mean this consistent, how to say, solution of the Boltzmann equation, right? The gamma S will be 0 if S equals 0.
Okay.
Right. On the other hand, the distribution function F with the Boltzmann distribution indeed makes gamma F 0, which is detailed balance. That was more non-trivial to see.
Yeah.
As you have, as you have done in your paper too, right?
Okay. Yeah. Thank you.
Okay. So next question by Dirk.
Yeah, thank you for this very interesting talk. So I don't have a question, but merely a comment. I mean, if the spin relaxation rate is on the same order as the momentum relaxation, that means that spin dynamics happens basically on the same transient time scales as shear viscosity, bulk viscosity, these things. So in essence, I think it would mean we really have to consider spin dynamics on that time scale. And well, the question is whether, I mean, the bad news is it makes everything more complicated, but the good news is it may explain why this equilibrium formula seems not to work for the polarization. Because if the spin degree of freedom is not equilibrated, then there's room for, let's say a solution to the problem. Okay. This is a comment, but of course, if you have your, please go ahead, Amil, if you want to say something.
Yeah, thanks for the nice comment. I think this is an important comment that I think essentially, I think we need to include the, say, some of the dissociative terms in the spin transport too, in addition to equilibrium. Spin polarization we are assuming in current hydro computation, right? That's your point. I think,
I mean, if viscosity is important to understand collective flow, then this spin relaxation is important to understand.
Yes,
But actually, I wonder whether there's whether you intend to also include spatial gradients, because somehow you seem to relax only by spin exchange, no? Because there's no, at first sight I would think there's no orbital angular momentum spin angular momentum exchange at this point. So maybe, I don't know, or maybe I understand. Is that true here in the calculation?
Yes, so that is true. So in the beginning of my talk, yes, I pointed out our limitation that indeed we are not really including the vorticity effect here due to the technical issue of difficulty of these non-local collision terms that you are working on now.
I wonder whether it helps to equilibrate spin faster, but okay, well, this is, I guess, what else.
Yeah. So indeed, that would be kind of one of the most impending important question to be addressed. It's just technically seems quite challenging to really include H-bar corrections in this QCD collisions.
Yeah, but it seems that you have solved this with the spin sums there. I mean, that would also be interesting to understand. You were talking about this some bottleneck, and then it took you a while to understand how to do it. Maybe that would be very helpful. But I guess it's in the paper. We can find these details in your paper, or
yes.
Okay.
So you can find all the details in our paper. Yeah.
We'll take a look.
So hopefully that would be helpful to really.
Thank you very much. Thank you.
Yeah. Thank you.
Okay, so next, Enrico.
Hi. Actually, my question is related to what Dick just said. So, does the Lindblad equation change if you include orbital angular momentum, or is formally the same? This may be a naive question, but so the one that is here.
Oh, you mean this part? Yes. Yeah, I think as we discussed, this spin orbit coupling should modify our relaxation term gamma in such a way that in equilibrium, the density matrix relaxed to the new kind of modified density matrix with vorticity spin coupling. Are you asking whether it also modifies this Hamiltonian evolution
yes,
part
because
as well?
yeah, because if you then, when you have the equation for the spin, it seems that the angular momentum is not conserved, right? Because the spin, I don't know, the spin just
right.
So I'm not sure, but just seems that should be modified, but I don't know if it's.
Yeah, I think this is also a very important question, and I think after we kind of after we work out everything, including this non-local effect, then we will be able to see whether it also appears in this Hamiltonian evolution part or not.
Mm-hmm.
So I think at this moment I don't know a priori whether it should or should not appear in this Hamiltonian evolution part. Yeah.
Okay.
But one thing we know is that the EM part, electromagnetic field part, interactions do appear in H0 part. So presumably there might be some other. There also will be some effect from vorticity to H0 part.
Okay.
I guess. Yeah.
Okay. Can I ask another quick question?
Yes.
Go ahead.
When you take the massless limit, you said that you get this separation, right, between chirality plus and minus. But
yes.
The spin that the spin operator that you are considering doesn't have this trivial massless limit, or does it? Because when you just consider the spin vector as you take it, as far as I understood from whatever the canonical, right? I think, but you say that you can do anything in principle.
Yes. So let me see.
But that doesn't. This is not a good definition for spin for massless particles, because.
That's also a good question. So I think I should have mentioned that point also. So here, the answer to that question is in the middle. It's most convenient to use the helicity basis. So we are working in the helicity basis. And one reason to work on helicity basis is that it has a smooth limit to the chiral massless limit.
For the spinners, but for the operator, I don't know. Yeah, okay, I have to think.
So, right. So the state, this spin state here, are written in the helicity basis. So there's a P and helicity 1, P helicity minus 1. In the massless limit, the only thing happens is that they decouple. These equations between them decouple. But the formalism still makes sense.
Okay.
Yeah. Okay. So that's one usefulness of working in the helicity basis, I think.
Okay.
Okay. So one last question by Jun, and then.
Very nice. Thank you.
Yeah. Okay. Thank you.
Yeah. My question also is related to the Enrico's question. So you use the helicity basis. It's an advantage that you can smoothly transform to the massless case.
Yes.
But is it possible for you to consider another basis, for example, along the fixed direction, for example, y direction? Then you look at the initially
Right.
you have polarization along the y direction. Then after some time it is disappear.
Yes, I think that's also a good question. Yes, I think in principle that is possible, although that it may not have a smooth massless limit, but for massive case, I think it should be possible. What could be very difficult to work in that basis is that the spinor summation that we have to do in this, where is it? Yeah, here. The spinor summation in that arbitrary basis would be, I think, almost
maybe
impossible.
more complicated.
yeah, would be almost impossible, I guess. Well, I mean, you might be able to do. I mean, you have more, I think, power to do that.
Yeah, if you consider this problem, the spin polarization along the fixed direction, it is more, I mean, closer to the real problem. You can see that
Well, I have slight disagreement on that because, as I said, from our density matrix, you can compute any other definition of spins just by multiplying some transformation metrics here. So, I mean, changing basis should also correspond to multiplying some basis change metrics.
Okay.
So I don't see that's really a matter of. I think that's just a matter of easiness in the computation rather than a fundamental issue.
Okay. So, another question. Yeah. Do you have an estimate how long is the relaxation time?
Well, we only have a parametric estimate. Well, everything is given in our final relaxation operator expression, but I can only say that it's just parametrically given by g to the 4. So in recoupling limit, it has the same order of the shear viscosity as Dirk said before. That's the only thing I can say. Yeah, I don't know numerically how large or small compared to other transport coefficients. Yeah.
Yeah. Okay. Thank you.
Okay.